Hi, everyone. So this is the beginning of a new series. I promise I'll try not to let this distract me too much from the other series that I know a lot of my followers are interested in. So, well, first, let me introduce to you my friend Steven. If you want to say hi.
Hello there.
Yeah. So, basically what's going to happen in this series is we're going to talk about analysis. We're going to talk about how to define the real numbers. What are sequences? What are series? What does it mean to converge? We might even talk about the p-adic numbers. I don't know where this series is going to end. We're just going to start talking. I should say that the main goal, if I'll link it here, if anyone's not seen the little animated video that came out from the Summer of Math Exposition video on this channel last summer. I talked there about this whole thing about 0.9 repeating equaling 1. And I've been having conversations with Steven recently, and that topic came up, and he really wants to understand it, and has some tensions, with the concept, with that idea. So I thought it would be a fun way. It'd be one, I could just explain it to him, or we could turn this into a series together where now you get to see the learning process. So this is all going to be real time, me teaching him and maybe giving him a little bit of homework here and there. And hopefully, what I hope for you to get out of this is to follow along in this learning process. Whether if you find yourself moving faster or slower than our pace, that's totally fine. You can just sort of check in whenever. But I also want you to sort of experience the learning process, and hopefully there'll be mistakes that happen and successes that happen, and you'll be able to see that it's okay and in fact essential to make mistakes, but also what it's like when you have the aha moments and that great feeling when those things click. So with that all out of the way, well, let me first just ask. So Stephen, I gave you the other day a couple suggestions of textbooks, if you wanted to follow along on your own and do some reading on your own. And you spent some time looking at some of those?
I started working on the first one and I read it from the beginning. And then you and I spoke, and I started reading it from the first section on sequences, and then
Okay,
realized that some of the nomenclature was still a little bit foreign to me. So I went back and just continued to read from the beginning.
great.
Lots of basics of set theory. And I've watched a lot of videos on set theory from various creators online. So that's been the amalgamation of my understanding thus far. So some of it's definitely making sense. Other stuff, not so much at all.
Perfect. Perfect. So I'm going to put that book I'll put a link to it, if it's freely available, or just the title in the description below. And with that, let me say to you, and also to the audience who's watching, if you have questions, the best thing to do is write them down. And so Stephen, as we go through this session, one of the things we might do is, before we begin with each lesson that we do, perhaps you can come to me with some questions, and we can talk about some of those questions first, because that's an essential thing. Is like, here's general advice too for the people watching at home. A great way to be successful in a mathematics class is to come with questions in mind, right? If you read some of the material ahead of time, then you're not seeing it for the very first time in lecture, right? And you might actually have a better chance of understanding it as it's being explained and able to ask those questions actively. And so I encourage the audience to also think of questions, leave some in the comments, and I might either just address them in the comments, or some of them I might address here in these sessions. So with that said, I mean, you mentioned that there's some nomenclature and stuff that you're unfamiliar with. Um, do you have any questions off the top of your head about certain things, or should we just dive into like what we're going to start talking about?
I'll mention one thing, and that is that when I started seeing element with a minus sign next to it, that started to mess with me a little bit because I wasn't thinking about element as a variable. I was used to seeing plus or minuses with X, but now we're seeing that little E, suggesting that something belongs to a set. This is an element of a set. And
Uh-huh.
so that showed up. And for some reason, that was a bit confusing, but that was when I jumped ahead. So I sense that
Okay.
if I were to go through, I guess the whole set of chapters up to that point, it would have been much more clarified. So I sense that we should probably just start at the beginning where you wanted to start.
Okay. Okay. So we'll just start at the beginning. But next time what I'll do is I'll have the textbook ready on hand, and then I can just share my screen, and then it'll be easy for us to discuss content in the textbook and talk about questions you might have about it.
Absolutely. Yeah. I'd love to do that.
Great. Great. So let's begin. I mean, the whole thing about, the goal is to understand this point 0.9 repeating equals 1. And is this the shared whiteboard?
I can see it now. Yeah.
Okay, great. But I don't know if you can draw on it. Oh well, we'll discuss. We'll work on. We'll figure that out in a second. So just to sort of start at the end of our journey for a second, right? What are we trying to ultimately the primary goal of this learning series is to understand the statement 0.9 repeating equals 1. So in order to understand that, we need to understand basically three things. We need to understand the number 1, which might seem silly. It's like, oh, 1 is 1. But as some viewers of my channel might know from my set theory videos, such as yourself, it's kind of weird and tricky how to define the natural numbers formally in set theory. So we might dip into that, but we might take it as given, and I might just suggest people go watch those videos about how it's defined. We also need to understand what 0.999 repeating even means, because a lot of people think they know what it means. They have an intuitive idea from what they were told it is in high school. But most people don't actually know what this means. This is just a shorthand for something called a Cauchy sequence. So in fact, even more. So here's just some buzzwords that if Stephen, you or if any of the the audience watching wants to read ahead, right? That can also be a great way to learn, is if you flip ahead to the part on Cauchy sequences and you look at it. And the first time you look at it, the definition's not going to make sense to you. Probably, right? It just won't, right? But it can be useful to sort of see squint at the horizon and see what's coming on the horizon, right? So not only, it's not even just a Cauchy sequence. Well, 0.9 repeating itself is a Cauchy sequence, but more generally, it's a Cauchy sequence representing an entire equivalence class of Cauchy sequences. Again, this is in my set theory videos. But there it's the more abstract version, right? It's like equivalence classes. I think I give some examples, but it's equivalence classes in a pretty abstract sense. So could be worth watching that, reviewing it. Stephen, I'm not sure how, I think you're feeling pretty comfortable about equivalence classes right now, right?
They need to satisfy 3 criteria. I know what those criteria are. Rigorously, how to prove them, on the other hand, something I don't understand, but I do know what equivalence classes refer to. Yes.
Right. So, I mean, this is going to be a great way to dig into that, right? Because like it can be fun to just learn some abstract theory and definitions for its own sake. But it's often more illuminating to do it in context. And now we see, okay, we really have a motivation to understand an equivalence class and be able to prove things about it because we want to be able to understand this statement. And in fact, there's a little bit more going on is equality. There's something to understand here too. You know, we think, oh, equals is equals. If they're the same thing on both sides, that means something. But it's, you know, there's different kinds of equality. You can have equality of different sorts of structures. So we'll dive into that later on. But the first thing to understand, sort of the most fundamental thing, you know, why we're here, is to understand the idea of a sequence. So probably most people are, you know, somewhat familiar with a sequence. Roughly, it's just an infinite, I should say, if this word doesn't mean anything to you, it's okay, but I should say it's a countably infinite collection of numbers. Well, what even is a number? What is countably infinite? Okay, we'll sweep some of those things under the rug. Let's get a little formal first. So we're going to take it as given that everyone understands the rational numbers. The definition of this is also complicated. It does involve equivalence classes, right? Because the rational number 4 divided by 2, we say it's equal to the rational number 2 divided by 1, right? Which we, as a shorthand, sometimes just write 2. That's actually an equality of sets, an equality of equivalence classes. So technically there's something non-trivial going on there. Stephen, if you think it would be beneficial for yourself to dive in, or if some of our audience members would like to hear more about that, let me know. And perhaps in future we can dive into that. But for now, we'll just take it as given our normal basic intuitive understanding of rational numbers. Sounds good?
Sounds good. Yeah. So far, so good.
Okay. And please, at any point, if you have questions, interrupt me.
Sure thing. I'll take advantage when it's necessary. I won't just pretend I understand when I don't.
So a sequence is really and more particularly an ordered countable list of numbers. So those are still mathematically some vague terms, but we're going to make it more and more precise. So it might be something we might call it A0, or maybe we start at A1. So A1, A2, A3, etc. And what would be an example of a sequence? Well, we could just have the sequence that goes 1, 1, 1, goes on forever. So we would call this a constant sequence because every term is the exact same. But there are some more interesting sequences of rational numbers, right? I could have the sequence that goes 1, 1 over 2, 1 over 3, 1 over 4, etc. Or here's a famous one that lots of people like. We have the Fibonacci sequence, right? So it starts off 1, 1. Oh, am I just writing a constant sequence again? Oh, no. Okay, the numbers change. 2, 3, 5, where I'm just, the next term in the sequence is determined by the sum of the previous two, right? So we have this whole zoo of sequences of rational numbers, and they can all look, you know, fairly different from each other, right? We can even have, you know, I guess I've written it in such a way that suggests they're all positive. Of course, I can have different sequences that are all negative, or maybe it flips between positive and negative. So we can have all sorts of sequences. But let's make this ever so slightly more precise. So for us, because we're going to do probably lots of dividing by n, I know I might set the internet ablaze with fury by saying this, but for us, the natural numbers are going to begin at 1. It's going to be the numbers from 1 on. Many people, Stephen, I don't know if you know, but many people have strong feelings about the natural numbers beginning at 0.
And I guess how that differentiates from the positive integers and that whole conversation, I suppose.
Yeah, so some people would be happier to call this set something like Z plus, because this is the positive, this is the same as the set of positive integers. But it sort of depends on what you're doing. It depends on your field. This isn't the first, and it certainly won't be the last time in mathematics people disagree on the right definition of a symbol. It doesn't really matter as long as you know what context you're in. So for now, I'm going to, when I write the natural numbers, I mean, we start counting at 1. This is common in analysis because often we divide by a natural number, and it's just easier because we avoid having to write something like take a natural number except for 0. It's really just a convention born out of laziness. So for us, here's one formal definition of a sequence. So a sequence is a function f from the natural numbers to the rational numbers. But that looks a little bit different than the stuff I wrote on the other page, right? I mean, we sort of wrote this A1, A2, A3, ... and I had some sort of like list of numbers. It could be just the natural numbers in order or something like this. So how do we connect this intuitive picture that we've been writing with this formal definition? Well, here's one way. So let's consider the sequence we had where A sub n was defined to be 1 over n. Right? So that was the sequence A1, A2, A3, right? Where if I wrote it out, so this would be 1, this would be 1 divided by 2. It's just 1 divided by whatever the index is, right?
Right.
So how do I get from this list, which is intuitively easier to understand, to this function, which is more formal and therefore makes it easier to make rigorous proofs with? Well, what do I need to do? What does it mean to be a function from the natural numbers to be the rational numbers? It means that I need to, for every rational number, I need to be able to prescribe, for every natural number as my input, I need to be able to prescribe an output of the function at that Q. So here's what I'm going to do. Here's how I'm going to define a function in the way that I normally tell it. Well, in fact, Stephen, I might even ask you. So I have this list of numbers, a sub n, that depends on some index, which is a natural number, and it itself is a list of rational numbers. And now I want to define some function that spits out, that eats a natural number and spits out a rational number. And somehow this should be closely associated to my sequence. So do you have any guess as to how we might do that? There's no wrong answers. No wrong answers here.
I'm feeling like there might be an inverse involved in this case. Like, is there a to the power of -1 involved somehow?
Technically, yes. Technically, yes.
Yeah, I'm not sure how to write this as a function.
So all I need to do, right, to define any function, right? Like right now, it doesn't, I mean, who knows what kind of function we're writing, right? To define any function, all I need to do is figure out some rule that depending on this n will spit out some rational number. And I do want this to somehow be related to my intuitive notion of a sequence here. So what can I do? Well, I can define this function so that the function evaluated at n spits out the nth term of my sequence. So if I did that, let me ask you, what would my function f evaluated at 3, what would that give me? What's the result there?
If we're using what we have above, that would be 1/3.
Exactly. Yeah. Right. And this is a function, right? This is just for each natural number, it's spitting out a well-defined rational number, right?
Sure.
Now, how would I go the other way, right? Because we've seen just now that I can start with my intuitive idea of what a sequence should be as just some sort of list of numbers, and I can rewrite it as a function from the natural numbers to the rational numbers. So now I want to go backwards. Let's say that we started with a function, and just to not get confused with the previous case, let's say I started with a function that ate natural numbers and spat out rational numbers. And now my goal is to define a sequence, which is, so some sequence, let me say that we sometimes write sequences as little sets like this. So we say B sub n to tell us that our sequence is depending on some index n. And we put these little curly braces around it with symbols indicating that the indices start counting at 1 and they go up increasing by 1, and we just don't stop. That's what the infinity means, right? So suppose I have some function, right? Let's say to make things more concrete, let's define my function. So maybe I have the function that takes in n and it spits out n squared. So can you think of a way that we might define a sequence of numbers, b1, b2, b3? So basically what I need to do is I need to give some rule so that for each n, I can tell you what the nth term of my sequence should be. And keep in mind, we want it to have something to do with this function g.
Right. Well, I know what this sequence looks like, generally speaking. It's 1 and then 4 and then 9. That's what, if we're using the natural numbers or the positive integers to define each b1, b2, b3. But how to put that, I'm not exactly sure what you're asking me to do.
So, well, maybe it'll actually be easier if we go more abstract for a second. So what I want, so now I just have g. I don't know what it looks like, but I have a function, right? It could be the function that takes in n and spits out n squared, but it could be any sort of other wild function, right? And now, so I have a function, and I want to somehow use that function to define a sequence in the intuitive sense, that is a list of numbers, right? And so what does it mean to define a list of numbers? Well, I just need some sort of rule that tells me what the nth number in that list is going to be. Can you think of some way I might be able to use the function g to define that nth term in the sequence, keeping in mind g eats natural numbers n?
Is this just not the inverse of what we had before, where b of n or b sub n would just be g as a function of n?
Yes, exactly.
Okay.
Right? It's just the
Right.
inverse of what we have before. And that makes sense, right? Because we want to be able to go backwards, go back and forth between our intuitive definition of sequences as lists of numbers and our more formal definition of a sequence as a function. So that's you're bang on. We just want to do the reverse process, right? And we can. This is a thing that makes total perfect sense, right? So one last comment on this whole function sequence thing. I just want to say, so when I write it like this other notation that's very useful, it's not so clear that that's either of the things that we've talked about so far, right? It might be more believable that it's some list of numbers, but like this is a set, and like this is a function. So how do we reconcile all of these things? Let me just quickly say that, I'm going to plug my set theory videos, or there's other set theory videos on YouTube that are very good too. I might link in the description that go further than my series. But a function between two sets A and B in set theory, even though we, think of this map or this machine that eats things in A and spits out things in B, its formal definition is actually a subset of the product of two sets. So you know what, I'm not going to go into more detail about that here, but if you're a little weirded out about the connections between all those things, that might be good material to review. Right. Okay, how you doing?
Good. Feeling good that I was able to give a satisfactory answer.
Great. Yeah, doesn't it feel nice when something clicks?
Absolutely.
And here's a little other lesson, for everyone. Notice when I first asked the question, you had no idea what I was asking you, and you were like, and you said that. This is why in a classroom environment or wherever, I know it's scary, especially in math. You don't want people to think you're dumb or something, but it's important. If you don't even understand the question, and then how can you answer it? You need to say something, right? You got to say, hey, look, I don't understand the way that you asked that question. And then I rephrased that question, and all of a sudden the answer became a lot more clear, right? So teachable moment. Okay. So what are we here to talk about now? So we have this idea of sequences of rational numbers, and a really important thing in the foundations of calculus, but also in everything that we're going to start talking about, is the concept of a limit. And so, in short, a limit asks about what the long-term behavior of a sequence is. So, for example, if I just have the sequence that goes, well, let's think about the sequence of squares of numbers, right? So this is the sequence b sub n, where it's equal to n squared. So this goes 1, 4, 9, etc. And we can ask ourselves, well, what happens to the sequence in the long term, right? Well, the numbers are getting bigger and bigger. Hey, let me switch gears for a second. Let me just talk about the constant sequence, right? So it's just ones forever, right? So what's happening in the long term? Well, nothing, right? I mean, what is this sequence going to be at the 40 billionth millionth term? What number is that going to be?
It's going to be 1.
It's going to be 1, right?
All day long.
So all day long. And so, we want some sort of way to express that. But, how do we say that precisely? Like, we could try and say that, like, the infinitieth term is still 1, but that doesn't make sense. We don't have an infinitieth term, right? There's only terms for each natural number, and infinity isn't a natural number. So already, even for the most like bland, basic, boring sequence, we're really going to want to have some sort of way of being formally precise about the long-term behavior, right? So now let's come back to the sequence about n squared. So what's happening in the sequence long term?
It's staying the same. Or were we talking about the first one now?
The first one, yeah, the first one. So 1, 4, 9.
It's just
Yeah.
increasing uh, as just 1, 2, 3. It's just the natural numbers. N is just the same as the natural numbers, and you're just squaring it. Not
Yeah.
sure.
Yeah. So
Answer.
it's yeah, but that's right. It's getting bigger, right? And
Right.
it's getting bigger, even, sort of in some sense faster than just the sequence 1, 2, 3, 4, right? Like it's getting really big. So how do we talk about that rigorously? Because with the sequence of ones, we already went, we sort of wanted to say something like, oh, the infinitieth term is 1, but that's nonsense, so we can't say it. And now, how do we talk about, like, let's pretend for a second it made sense to talk about the infinitieth term. Well, what would the infinitieth term here be?
You couldn't define that. I mean, it would be
No.
infinity squared.
Yeah, it'd be like, what? That's nonsense, right? Like that's just nonsense. We don't have a language to talk about that, right? So here's sort of part of what the concept of limits allow us to do, right? So limits offer us a language to talk about the long-term behavior of sequences. That's part of what they do. This is also sort of, an important thing because for some sequences, like here, things just don't make a lot of sense altogether. Like this one doesn't make sense. This one, at least, okay, we can say like every term is 1, it's 1 forever, and these are kind of vague, but there's a sort of thing. Yeah, I don't know. But there's other interesting stuff that goes on, right? So right now in the series, I'm sort of going to go back and forth between pretending real numbers already exist and ignoring that fact.
Okay.
Well, you know what? No, I'm for now, we're going to pretend the real numbers don't exist yet, right? That's one of the things. We're trying to build real numbers. We're going to
Okay.
try
Yeah.
and construct real numbers from the rational numbers and define them, because that's another thing. So I talked about can I go back slides here? Yeah, right at the beginning, this is a statement like this equality, and this is tied into the questions of Cauchy sequences, equivalence classes, and equality. What even is a real number? Like, we say a real number is a number that's not rational. But then what's a number? Like what's a general definition of a number? We need to sort of corral it into some zoo or something, right? So uh uh we want to be able to even talk about the definition of real numbers, right? So for now, we're going to pretend that we don't even know what a real number, pi square root 2, whatever. What's that? Here's a sequence that we already considered with some more interesting sort of behavior. And this might be a little tricky. Let's see, Stephen, if you have an idea of what's happening here. So let's think about this sequence, right? Now what's happening sort of long term? Let me just first ask you the easy question. We've seen a sequence where it stays the same. We've seen a sequence where things are getting bigger. what's going on in this sequence that you can notice, sort of long term? Is it shrinking or
It's
growing?
getting
Or
smaller and smaller.
is
And based on the little knowledge I have about such things, this,
uh-huh.
as it approaches infinity, converges to zero, right?
Ah, yes. Yes, right? And because we can see, right? So what does that even mean? And this is going to help us start narrow in on the right definition of what a limit should be, of what the right language is to discuss long-term behavior of sequences. So we're looking at this and we see that, yeah, it's getting smaller and smaller. But let me ask you this. Will these numbers ever be negative?
No,
No.
because they're all positive integers in the sequence thus far. We have no reason to just introduce negative integers, right?
Yeah. Well, I mean, in fact, we can prove that it's always going to be positive, right? I mean, our basic rules of arithmetic, right? We know for every natural number, right? For every natural number, n is greater than or equal to 1, right? And because it's greater than or equal to 1, we also know that n will be strictly greater than 0,
Right.
right? So what I can do here is I can divide both sides by n, and I'm left with n divided by n is greater than or equal to 1. Wait a second. What am I about to write here? I was about to write some nonsense. Aha. I made a bit of a superfluous comment. The thing we're interested in here is this: the fact that n is that 1 is greater than 0, right?
Right.
Pretty uncontroversial fact. But it's also important that we know that n is greater than 0. Why? Let me just say that if you have a number, say a, that's less than 0, and you had two numbers, x less than or equal to y, if you divided by a, the minus sign would flip around, right? Or sorry, if you divide by a negative, the inequality flips in the other direction. So just reminding everyone of that basic rule of arithmetic, right? It's like if I had uh, 4 is less than or equal to 8, right? But now if I divide both sides by -2, I look, well, 4 divided by -2 is
-2.
-2. 8 divided by -2 is
-4.
-4. Right. So if I divide both of these by by -2, and I'm going to write this down here and I compare them. Now I have -4 on the right and I have -2. Well, in order to make this statement true, I have to flip the inequality around, right?
Right. Gotcha.
Make sense?
Yeah, that makes sense.
Okay. Yeah. So this is why I wanted to mention that not only do we have, the fairly obvious fact that n is greater than 0, but that 1 is greater than 0, but we also know that n is greater than 0. So we know that when we divide both sides, the inequality is preserved. But what's 0 divided by n?
Don't we call that undefined?
Nope. It's not undefined.
0 over n. Oh, it's 0.
It's just 0. Yeah.
Yeah, sorry.
So remember for us, n is not 0. So it's always okay to divide by it. So 1 over n is strictly greater than 0. So we see, yeah, no, so we just formally proved, right? Never mind sort of looking at it and figuring, which is good. It's an important part of the mathematical process. Yeah, but we just used a formal proof to show that for all n, 1 over n is greater than 0. Right?
It has to be. Yeah.
It has to be, right? So we know that our numbers are getting, let me write our sequence again over here. So we know that our numbers are getting closer and closer. Well, they're getting smaller and smaller, but not so small, right? They're not going off to negative infinity. There's some sort of bound on how small they can get, right? So we know that definitely every term in our sequence, right? So a sub n is greater than 0 for all natural numbers, right? This means for all little n in the natural numbers, right?
Right.
So, okay, but we can ask ourselves now, are there other numbers that our sequence is always bigger than, right? I mean, vacuously, yes, because we know if all of the a sub n are bigger than 0, then they're all bigger than -1,
Mm-hmm.
right? And they're all bigger than -47, right? So there's a lot of numbers that all of these terms are bigger than. So it's at least all the let me know if you're familiar with this notation, but the half open interval from minus to infinity up to and including 0, anything in here, every term of our sequence is bigger than that.
Right. Because we're stopping at 0.
Yeah, we're stopping at 0. But here's the question. Do we have to?
No, we've just decided to.
We've just decided. It seems like we've just decided to, right? Maybe there's some other number that eventually our sequence just doesn't get that small. It would have to be a positive number, right? Because we've already accounted for all the numbers minus infinity up to 0,
Right.
right? So I don't know. Why don't we try something, right? So can you give me like a really small number that's positive?
A really small number that's positive. Does this include fractions? Are we talking about?
Yeah, it could include fractions. Yeah.
Okay, 1/1,000,000,000.
Okay, 1/1,000,000,000. So that's oh gosh, how many
9 zeros.
yeah. 1/1,000,000,000. Okay. Well, let's check, right? Let's think about this for a second. Is there any term that belongs to our sequence which is smaller than this? Or here's a better question. Is every term in our sequence strictly larger than this thing?
No.
No.
We would find the billionth and a first term, the 1 billionth and first term.
Yeah.
Yeah.
Yeah. The 1 billion and 1th term of the sequence, right?
Yeah.
It's strictly smaller. So this would be 1 billion and first term, right? Because well, why? Because this is literally 1/1,000,001, and that is ever so imperceptibly smaller than this number, right?
Right.
Okay, wow, 1/1,000,000,000 is pretty small. You know, if you plug it into your calculator, it's a bunch of zeros and a 1. Okay. Well, what about an even smaller number? What's an even smaller number than 1/1,000,000,000?
1/10 trillion.
Right. 1 over, I'm not even going to write all the zeros, right? I'm going to
Yeah.
write 1/10 trillion, right? But what about that? Is all the terms in our sequence, are they going to be strictly larger than that?
No,
No,
it just keeps going.
it just keeps going, right? So it definitely seems like zero. So here's a guess. We don't know this is true yet. We haven't really done a very formal proof, but our guess is this, that zero is the largest number which is strictly less than every term in the sequence A sub n. So that's our guess, right? And okay, that's our guess. But there's more work to be done, right? Like, so for instance, we know, for example, that all the other numbers, like given any number of the form 1 over m, can this possibly be smaller than everything in our sequence?
Can this be smaller than everything in our sequence?
Yeah, for some m. I'm just saying pick a natural number m.
Well, we're just substituting out the variable
Yeah.
m for n, so then the answer should be no, right?
No, right. So what's an example? What's an example of a number that's strictly smaller than this and in our sequence?
-1, or no, in our sequence,
Yes, in our sequence.
smaller than 1 over m.
Yeah.
It needs to be smaller than that.
Yeah.
1 over m minus 1.
Close, not -1.
But
so what did you do to a billion to get something that was smaller than 1 over a billion?
I minused. Oh no, I added.
Yeah.
Sorry, yeah, because we're using fractions.
Yes,
right.
exactly. Yeah,
it's already
confusing.
inverted.
It's confusing because it gets flipped around. Yeah.
Yeah.
Yeah. So we know this, right? We know that all the numbers of the form 1 over m, we know for those, none of those can be smaller than everything in our sequence, right? But the problem is there are other very, very small numbers, right? We haven't excluded the possibility that there's other very, very small rational numbers that are less than everything in our sequence. What if I have something that looks like 2 over 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 3? Right? So our thing in the denominator is an odd number, so I can't cancel that 2 out, right? How can I be sure that now it's a little bit trickier. How do you find some number of the form 1 over m which is strictly less than this?
Do you still need that denominator involved? Like, does it need to be replicated somehow?
Maybe. So here's what I'm going to do, because we're almost at the hour mark. We started a little late, but let's not tire ourselves out on day one. We're going to call things here, and I'm going to leave everyone with a bit of homework. So let me give you this hint, right? All you need to do, you're trying to find an m that makes this true. So I'm going to suggest to you, and if you want, you can, instead of writing out all these zeros, you can just call this alpha for short, right? Like invent a variable name so you don't have to write out all these numbers. But what you can do is do some algebra to solve for m. Or rather, what's going to happen is if you manipulate this expression in the right way, you'll get something that looks like m, greater than, or maybe it'll be less than, who knows, m greater than some stuff here. And then all you need to do is come up with a natural number that is greater than whatever that is there, right? Because if you pick any natural number that's bigger than the stuff on this side, well, that natural number will work.
Right.
So here's homework for Everett. So let me just make a list on the screen. So homework number 1 for everyone. I'm going to share the name of the textbook below. Homework number 1, read ahead. Look at some things you don't understand, get confused, get lost, get inspired. Homework number 2, have questions for next time. Homework number 3, solve for m. I mean, I say solve for m, there isn't going to be a unique m that works, right? What I mean is find some m, at least one, that makes this thing true, right?
Okay. And for the questions, how closely pertaining to this must they be?
I mean, if you want to read all the way ahead and look at a textbook on advanced category theory applied to quantum information theory, by all means do that. But, it's probably more worthwhile to look at the textbook and to, only go a little bit ahead, but don't let me restrict you, right? You want to go to the last chapter and see where all this stuff is heading, like long term, and you see some fancy symbols that catch your eye and you think are cool. Yeah, go ahead and look at it. Google some terms or something. If you don't understand everything or anything, that's fine. But just explore a bit. It's important to explore. It's important to not understand.
Okay, totally.
Let me add one last thing onto list, because I'm going to ask. So it'd be really great to at least take a stab at these 3 things. This last thing, by no means like this is bonus. Here's a bonus question on the assignment. Once you do this, start thinking. I know it's going to be, if you're not used to proof in the abstract, it'll be difficult to think about, but think about how to prove / find and m so that given any rational number which is greater than 0, you can always choose an integer to make this true. Right? Because what will that do? What will that do for us? Why do we care? Remember, we saw that this whole chunk of numbers was all those numbers had the property that they were smaller than everything in our sequence A sub n, strictly smaller. And we stopped at 0, and the question was, did we have to? Was that an artificial choice? Or does it so happen that 0 is the biggest of the smallest numbers?
Okay, the biggest of the smallest numbers.
Yes.
Okay, gotcha.
Yes.
Interesting way of looking at it. I like that analogy.
So just some things to think about. Thank you, Steven, so much for joining me on this journey of discovery. Thank you, everyone, for watching. Please feel free to say stuff in the comments. Yeah.
No, this is a lot of fun. I'm really glad we're doing this. I'm having a great time.
Awesome. Okay, well, take care, everybody.